Parametric equations and calculus. Well, parametric equations have graphs. And what do graphs have? Well, they have slopes, slopes of tangents. Don't those graphs still have slopes? So they have derivatives and areas. We'll get that later on. But for now, yeah, we need to start here talking about the slope of a tangent line for parametric equation. X equals f of t, y equals g of t. Okay, here's the thing. Slope of a tangent is dy dx, dy over dx. In our normal way of thinking, we're thinking, well, that is the derivative of y with respect to x. However, that's Cartesian thinking. This is still going to be the slope of the tangent. However, thinking of it in parametric terms, both y and x are in terms of t. So here's what I have to do. For parametric equations, I'm going to do, for dy, I'm going to do dy with respect to t, and then I'm going to do the same thing for x, for the dx. I'm going to say that's dx with respect to t. In other words, the slope of the tangent line is going to be the derivative of this thing over the derivative of the x equation. That's what this means. The derivative of the y equation over the derivative of the x equation in our parametric. Because now both of those are in terms of t's. Okay? So let's find dy dx for x equals t squared minus 2t, y equals 3t plus 1. It's really not too bad. So dy dx, you just have to remember the order here, which is not hard because it's right there for you. dy dx is going to be, well, it's dy dt over dx dt, but dy dt is just the derivative of that with respect to t, which the good news is that's just basically power rule. What's the derivative of that with respect to t? 3. What's the derivative of that with respect to t? 2t minus 2. With me? It's just, yeah, just that the top is the derivative of that, the bottom is the derivative of that. It's not too bad. Okay? All right. Try this one. Find the slope of the tangent at t equals 2 for t squared minus 2t x equals t squared minus 2t y equals 3t plus 1, which is the same thing I just did, okay? So the slope of the tangent at t equals 2, well, the slope is dy dx, but in terms of parametric, it's dy dt over dx dt, which we just did is 3 over t, 2t minus 2. It's just the derivative of that, the derivative of the y over the derivative of the x. And so here I just want in particular the slope at t equals 2. We'll just plug in t equals 2, right? Yeah, usually when we get these dy dx's, they are in terms of t, so in this case we've got just what we need. T equals 2, so it'd be 3 over 4 minus 2. 3/2. Yeah. Slope of the tangent is going to be 3/2 at T equals 2. All right. Well, let's look at another little twist on this. Is that okay? All right, so find the slopes of, maybe more than one. Find the slopes of the tangent lines to the curve x equals t squared, y equals t cubed minus 3t at the point 3, 0. Find the slopes of the tangent lines to x equals t squared, y equals t cubed minus 3t at the point 3, 0. Well, obviously we start. Our slope is dy dx. But in this case, how do I get dy dx? Well, to get dy dx in this case, I do the derivative of y, which would be 3t squared minus 3, over the derivative of the x, which is 2t. The problem is here, I want a specific slope, and the slopes are given in terms of t. Do I know the t value? Nope. What does this give me? Well, this is x comma y, right? I don't know t. So that's the extra catch here. I don't know the t. The slope's given in terms of t. I don't know the t value I want for t values. How do I get them? Well, looking at the two equations there, I do know I want x is 3. Can't that help me over here? Since I want x is 3, don't I know that, and I know that x is equals t squared, can I figure out what the t value needs to be? Yeah. I've got x is 3, so just substitute that in for x. I've got 3 is equal to t squared, so that tells me, doesn't it, what I need to have for t? There's going to be two values, isn't there? It doesn't say t has to be greater than 0. T can be negatives and positives. Yeah. Square root both sides, plus or minus. Yeah. So t is the square root of 3. T equals or negative square root of 3. Okay, so what are the slopes I want? So at t equals square root of 3, and notice I can't just say plus or minus because I've got the cube thing there. Huh? Oh, I'm sorry. Ah, makes it a whole lot easier then. Oh, no, wait. X is 3. X is, yeah. I've got x is 3. I was right. Oh. Oh. Oh, 3t squared. Thank you. So this was all right. This was wrong. Okay. Change that to square. Thank you. All right. So at t equals square root of 3, we'll have the slope, the m, equals 3 times the square root of 3 squared. Oh, so, well, no, that. We might have, sometimes we can get, plug in both the plus and the minus, but here we can't because the bottom's going to be square root of 3 just to the first power. What does that give me? 3 times 3? 9. Minus 3 over 2 square root of 3. Just 6 over square root of 3. 6 over 2 square root of 3, which is 3 over square root of 3. And you can rationalize the denominator there if you want. That is one of my slopes. And then at negative square root of 3, it's going to be very similar. The slope is 3 times negative square root of 3 squared, minus 3, over 2 times negative square root of 3. All that's going to change is the sign. That was going to be negative 3 over square root of 3. So I've got two slopes. At the point 3, 0, how does that work? Well, I mean, you could probably graph it and look at it, but if you remember back at that one thing we had, say at 0, don't I have two slopes there? That's kind of what's happening. It's crisscrossing, so you get this crisscross action, and that's what's happening here. All right. Let me go ahead and talk with you then about the second derivative for parametric. This is a little tricky. First of all, just some notation. Second derivative, we usually write y double prime. Well, when we say y double prime, usually we mean the derivative of the first derivative, right? So d dx of the first derivative, would you believe that? That's what we mean usually. Second derivative is just the derivative with respect to x of the first derivative, which we could write dy prime dx. Yes, but isn't y prime also dy dx? So substituting dy dx for y prime, we have d dx of dy dx. Why do I write that? It's because this is the way a lot of books prefer to see this. The second derivative can be written, do you see here, d squared y over dx squared? Or just d without parentheses. See where that comes from? d squared, dx squared. Okay. So this last one that I came up with right there, that's the preferred, that's the way the book will write the second derivative for these parametrics, okay? We haven't used that notation much. Like I said, we like this notation, but for this case, this is what they usually write if they want the second derivative, okay? All right, so what about for parametric equations? Well, the second derivative. Well, let's said is usually if they're wanting the second derivative, they say what? Find this. Let's focus on this for just a second, though. It's the d dx of y prime, or the d dx of dy dx. In the parametric case, what is dy dx? Well, you've got two things going here. And I think that's why I did this. Okay, here's what it is. Let's go with this one. Forget that other. Okay? In the parametric case, what is y prime in parametric format? Isn't it dx, dy dt over dx dt? for parametric equations, y prime is dy dt over dx dt. Okay? Well, isn't this then parametric? Here's what I've got. If I go to parametric, in other words, the x is in terms of t, the y is in terms of t, isn't this what I would have? What does this mean? This is the derivative with respect to t of the derivative. And then this is the derivative of x with respect to t. It's kind of complicated. This is the derivative of the derivative. And then this is the derivative of x with respect to t again. Now, please note, when I do the derivative of the derivative, I've already done the derivative of x with respect to t, so I'm going to do it again. You'll see how it goes. Okay? But note here, for parametric equations, this is the second derivative. The derivative of the first derivative with respect to t over, you're going to do then an over the derivative of x with respect to t again. You'll see how it works. Okay? It's the derivative of the derivative with respect to t. Which isn't the second derivative, because we're doing a parametric. To get the second derivative, you have to divide it by dx dt. That's the whole thing. Okay? I know it's kind of confusing, but here it is. I'll show you. But that's what you have to do for parametric. Since we've got an x equation, we've got a y equation. That's what you have to do for parametric. Okay. All right, so here is one to try. Find d squared y dx squared, second derivative, for x equals t minus t squared, y equals t minus t cubed. Well, again, it just means the second derivative. And of course, to do any second derivative, what do you need first? First derivative. Okay. You need the first derivative first. Well, the first derivative, dy dx, y prime, whatever you want to say. How do we do it? Well, parametric, you just do the derivative of the y equation, 1 minus 3t squared. Almost messed up again. And then over the derivative of the x equation, which would be 1 minus 2t. Okay? That's easy enough. Pretty straightforward there. It gets a little trickier for the second derivative. So the second derivative, here's what I do. Second derivative, the d squared y dx squared. I don't know if you can draw that, but it's second derivative. Think of it, write it if you want to, in terms of the y prime. Second derivative is, how do we have it? dy prime dt over dx dt. Or even better yet, it's d dt of y prime over dx dt. That might be even a better way to write it. That's how you do the second derivative. Because I'm going to do the derivative of the first derivative, which is this, over dx dt. So how do I do that? Well, to do the derivative of this, I'm doing the derivative of that. How am I going to do the derivative of that thing I've got parentheses? Quotient rule. It's a quotient rule, isn't it? So this top line, by quotient rule, is going to be low, d high. So 1 minus 2t times negative 6t minus high, d of the low, which is negative 2, over low squared. All that is just the top. I still have dx dt. So I have to divide that again by a dx dt, which that's just going back to the original x equation. What is dx dt? It's 1 minus 2t. See the difference? We are doing another derivative of that. Here's what it boils down to. I need to do the derivative of that, which is the top. But what else do I have to do? Divide it by another dx dt. That's what it really amounts to. I've got to do the derivative of that, but then I have to divide it again by dx dt because we're parametric. We're in parametric here. That's really what this boils down to. Yeah, I'm going to do the derivative of that to get the second derivative. I just have to divide that by another dx dt. Okay? That's the way it works. Now, clean that up. I'm not quite done with that. I can make that look a lot better, I think, but I don't have room for it. All right, so let's see how we go. So that would be negative 6t plus 12t squared. Minus minus, so it would be plus 2, so it would be 2 minus 6t squared. And then the good thing here, most of these I think, we've got 1 minus 2t squared divided by, that's in the denominator, divided by 1 minus 2t. What's going to happen there? Well, let's do it this way. I won't cancel because it's divided by 1 minus 2t, which means times what? 1 over 1 minus 2t, right? So I can rewrite this as 1. Those are going to combine, aren't they, to be a cubed? What have I got? 6t squared minus 6t plus 2 over 1 minus 2t cubed.